Okay, hello again. This is the um, the rest of chapter 2. Hopefully we can finish it in this video. So I hope you're doing well. So let us get started. So we're going to talk about continuity and the precise definition of limit. This is what we want to do. So let's start with continuity. Now, continuity in algebra was defined kind of like if you can graph a function without lifting your pen, then the function is continuous, right? So we're going to put some kind of calculus theory under that instead of just saying, because it's not very precise, and so in calculus we like to use calculus to define continuity. So we're going to use the idea of limit to define continuity. So let's do that. So basically in calculus we say a function is continuous at a given point. Let me just describe it here. Suppose this is point A, and here's a function f of x, right? So we say that f of x is continuous at A, and then this is f of A, of course, right? If the limit of f of x when x approaches A from left and right, of course, when we say x approaches, which is two-sided limit, that means left and right, right? The limit of f of x when x approaches A has to equal to f at A. So this equation actually has three parts to it. First part is the left side, that is a limit. So the limit has to exist, otherwise it cannot equal to a number. It has to exist. So the limit has to exist, obviously. So that's one thing we are saying here. And the right side has to exist. What do I mean by that? I mean that f at A has to exist. That means A has to be, of course, not only in the domain of the function, but f of A has to equal to this limit. So another condition is that f of A has to exist. That means has to be defined. And then the third condition is that the limit has to equal to that f of A. So there are three parts to this. Think of it as left side, right side, and the fact that they have to be equal. Those are the three parts to this continuity definition. So a function is discontinuous at a point if it fails to be continuous at a point, obviously. Okay, so let's work a little bit more on this. So in this example, the first one, which one of these three conditions fails? Well, let's see. It looks like the limit exists, right? So if you were to take the limit of f of x at A, it would be this point right here, right? From left and right. So the limit exists. And then what is it that is not, working here? Well, the first one, because there is no point at A. There is no value of y at A is empty, right? So that means the first condition fails, so this function is not continuous at A. And what is going on over here? Well, let's see. Is the first condition satisfied? Yes, because f of A is that point right there, so exists. And the second condition is does the limit exist? Well, the limit doesn't exist because the left limit is somewhere over here, right? And the right limit is somewhere over there. So if you approach A from right, the limit is here. If you approach A from left, the limit is there. So the second condition is not satisfied. And here we can't really talk about the third condition if these two don't exist, right? So now the third one, well, let's see, the first one is satisfied because f at a exists. F at a is this value here. The second condition is satisfied because the limit exists. Limit from the left and right, both are the same right here, right? But the third condition is not satisfied because the limit is not equal to f at a, right? Now, this kind of discontinuity is removable, the third one. Why? Because let's say we have a function, right, that has a formula. We say, okay, let that function be whatever that formula is for all numbers not equal to a, and then for a, we're going to move this point and put it in this hole. So we can redefine the function with a little tweak, not much change, a little tweak, just saying that f at a has to be the same as the limit. We can make this function continuous. But this function is not removable because there is a jump here, right? This discontinuity is not removable. Discontinuity is not removable because f at a is not there. We cannot change the definition of f at a because it's not there. All right, so those are the three types of discontinuity. Let's look at some. So using the definition, determine whether the function is continuous at x equal to 3. Okay, so is the first condition satisfied? Yes, f at a is basically, so f at a here is 3, right? Because these pieces are polynomials, so they're continuous everywhere. You know, if they find the limit would be the same as f of that number, so they're continuous everywhere. But the problem here, the discontinuity, is at this breaking point right here that breaks the domain into two parts at 3. So does f of 3, is it defined? Yes. F of 3, we have to use that one, is going to be negative 3 squared plus 4, which is negative 9 plus 4 is negative 5. Now, does the limit exist? Let's see. What's the limit of f of x when x approaches 3 from left? Well, if it does from left, we have to use that part, which is just basically the limit of negative x squared plus 4 when x approaches 3 from left. That is equal to, of course, negative 5. We just talked about that. Now, what about a limit from the right? Well, let's see. What is the limit when x approaches 3 from right? Well, that we have to use the second part. So that would be limit of 4x minus 8 when x approaches 3 from right. Now here we just substitute, right? 4 times 3 is 12. 12 minus 8 is 4. So obviously they're not the same, right? So the limit does not exist. The second one fails here, right? All right. So the second one fails, and when you graph this piecewise function, you see that there is a jump discontinuity, right here. All right. Polynomials are rational functions are continuous at every point in their domains. Previously, we showed that if p of x and q of x are polynomials, then the limit of p of x is p of a. So that proves that no matter what a is, any point in the domain of the function would be the function would be continuous at that point, because you see the limit of p of x when x approaches a is always p of a. So polynomials are continuous everywhere in their domain, and rational functions also continuous everywhere in their domain, right? Whatever the domain is, they're continuous at that domain, at every point. So determine the points, if any, at which the function is discontinuous. Well, here, the only point that the function is discontinuous at, could be discontinuous at, is when the denominator is 0, right? So we're going to take e to x minus 2 and set it equal to 0. Then e to x has to be 2. Then we can take ln of both sides. So ln e to x equals to ln 2. So x equals to ln 2. So the only x value that you cannot substitute here is ln 2. Because if you substitute ln 2 for x here, you get e to ln 2 minus 2, and that would be 0. Because e to ln 2 is 2. 2 minus 2 is 0. Denominator is 0. So this has a discontinuity at ln 2, and that kind of discontinuity is called an infinite discontinuity. Again, is not removable, because this has what? This has a vertical asymptote actually at ln 2. So it's a discontinuity that is not removable, is infinite. Now here's another one. It says determine the point, if any, at which the function is discontinuous. Again, the only point that this is discontinuous at, the only points would be all the points that are negative and also 0, because it's in the denominator, right? So basically every point greater than 0 is good. Any point less than or equal to 0 is not good. This continues at all of these points, and this continues for all positive numbers after 0. 0.1, 0.2, 0.01, 1, 2, 3, whatever number greater than 0. Okay, so that's that. So we can say this is continuous in from 0 to infinity, not including 0. F of x, if f of x is discontinuous at a, then f has a removable discontinuity if limit exists, right? Note that when we state that limit exists, we mean that limit equals to a number, right? And that number is a real number. If f has a jump discontinuity, then the left and the right limit are not going to be, if the limit of the left and the right exists, but they're not equal, right? Then we have a jump discontinuity. So f has an infinite discontinuity if the limit goes to infinity when x approaches a, whether from left or right. It doesn't matter what infinity, as long as f of x approaches infinity when x approaches that number from left or right or both, then we have a infinite discontinuity. Okay, so here classify discontinuity of that as removable jump or infinite. So this is removable, this is jump, and this is infinite. All right. Now, if we have a hole and f at a is not defined, we could just define it and put it there, right? So if the limit exists, then we have a removable discontinuity, even if this is not there. We can actually put it here. All right, so what about this? Well, at 2, what's going on at 2? What we have to, first of all, is f at 2 defined? No, because it makes the denominator 0. So it has a discontinuity at 2. But what kind is it? Well, to find the kind, we have to find the limit of this when x approaches 2. So let's do that. Well, we have done examples like this. We see that if we have 0 over 0, then we're going to have to do something, factor something, cancel something to get rid of 0 over 0, right? Here, the limit would be 0 over 0 if we substitute 2 for x. 2 squared minus 4, 2 minus 2, 0 over 0. So if we factor x minus 2 and cancel it, then we get x plus 2, and the limit is 4. So there is a limit at x approaches 2. There is a limit. The limit is 4, right? But f at 2 is not what? Is not defined. So this is a removable discontinuity. So how can we remove it? Well, we can define f of x this way. We can say f of x equals to, let's say, x squared minus 4 over x minus 2 when x is not 2, right? And then we want f of x to be what at 2? We want it to be the limit. What is the limit? The limit is 4. So let it be 4 when x equals to 2. This way, this function would be continuous at 2. Why? Because the limit is 4. F at 2 is 4. They're equal. So it satisfies our definition of continuity. Okay? Determine the points, if any, at which the function is discontinuous. Okay, so here, again, what's going on here? Well, we have the denominator, which is x times x minus 1. And we know this is not defined at 0 or at 1. Why? Because 0 and 1 make the denominator 0. But 1 makes the denominator 0, but 0 makes the numerator and denominator 0. So we do have a discontinuity that is infinite at 1. Why? Because it makes the function go to infinity. So that one is infinite discontinuity. And then at 0, since we can cancel the x, the limit is going to be what? What's the limit of f of x when x approaches 0? Well, it would be 1 over 0 minus 1, which is negative 1. Right? So there is a removable discontinuity at 0 because the limit exists. Can we remove it? Yes, we can define it this way. We can let f of x be whatever we are given here when x is not 0 and when x is not 1. And then define f of x to be negative 1 when x is 0. And it's going to look like this. So this is the function without the extra piece that we added to this. This function would have a hole here. But since we fill that hole with this, then now it's continuous over its domain. All right. Continuous over an interval. If a function is said to be continuous from right, well, let's talk about right continuity and left continuity. Sometimes we have functions like, for example, let's say square root, right? So f of x equals to square root of x. Now, is it continuous at 0? Well, let's see. Our definition says that the limit of f of x when x approaches 0 has to be f at 0. But notice, we can't really find this limit because we cannot go to the left of 0 because this function is not defined for numbers less than 0. So what do? Well, we're going to define a limit from the right. We say, if this is true, then we say that f of x is right continuous at 0. What does that mean? That means if you take the limit from the right, that would equal to f of 0. So this is right continuous at 0. And if, of course, it's continuous for every other point after 0. So that's the definition of right continuous function. And because we could also have a left continuous function. For example, let's look at square root of negative x, right? G of x is the square root of negative x. So this function is actually left continuous at 0. Because you can't go to the right of 0, you have to be on the left of 0. So if I take the limit, it's going to look like that. So limit of f of x when x approaches 0 from left is going to be the same as f at 0, which is 0, right? All right, so that's the definition of left and right continuous functions. Example, state the interval over which the function is continuous. Again, the continuities here, the problem with the rational function is only the stuff that makes the denominator 0. What values make the denominator 0? Well, let's see. X squared plus 2x is 0, so x equal to 0 and x equal to -2, right? So two numbers this thing is not continuous at, so that means it's continuous everywhere else in the domain because it's a rational function. So we're going to go from -infinity to infinity, and so here's the number line. We're going to break it down into at -2 and at 0. So it's not continuous at -2 or at 0, but it's continuous here, it's continuous here, and it is continuous here. So we're going to write it as 3 intervals and put the union in between. So these are all the intervals that this function is continuous at, right? Over. It continues over all of these intervals. All right. A function is continuous over an open interval if it is continuous at every point in that interval. A function is, so if a function is, when we say a function is continuous, for example, over an open interval a and b, it means it has to be continuous at every point in this open interval, right? So a function is continuous over a closed interval of the form that, so closed interval means the endpoints are included, right? Then a function to be continuous at a closed interval, it has to be continuous in that open interval, and it has to be continuous, right continuous at A, and it has to be left continuous at B. This way we can say it's continuous in a closed interval. And you can see the rest of them, like this is, if it's half open this way, or if it's half open that way, we can say a function is continuous over this interval if it's continuous over the open one, and is right continuous at A. This function is continuous over this kind of interval if is continuous over the open interval and is left continuous at B. This has to be right continuous at A. This has to be left continuous at B. Okay? So that's the idea of left and right continuity and continuity over intervals. Example, decide if the function this is continuous at pi. If it is discontinuous, what type of discontinuity is it? Okay, well, pi, we know pi, tangent is what? Tangent is sine over cosine. So if you're over here, pi, tangent of pi is sine pi over cosine pi. But the sine pi is 0, and the cosine pi is -1, and 0 over -1 is 0, right? So tangent denominator is 0, and the numerator, of course, is not going to be at pi. When you substitute, sine of pi is 0, but the cosine pi is -1, right? So we get 0 minus -1 over 0, which is 1 over 0, and that's infinity. So this is an infinite discontinuity. That means theta equals to pi is a vertical asymptote, actually, because this thing goes to infinity, right? So it has an infinite discontinuity at pi. Right? So now, what is the limit of this? Well, if you go to pi to the left of pi, so let me do this again. So if you go to from left of pi, so these are angles smaller than what? Smaller than pi, and these are angles bigger than pi. So if you approach this way, here sine is positive, before pi, sine is positive and cosine is negative, right? So that means that makes tangent negative, right? So denominator, if I put something close to pi to the left of pi, let's say pi is 3.14, let's say 3.1, right? If I put this in here for tangent and sine and cosine, so what happens is that the denominator here close to pi, sine is going to be a small positive number. So that would be a small positive number, right? Minus cosine would be some negative number, right? So the numerator would be positive, and the denominator determines the sign. So would the sign be before pi? Well, tangent is sine over cosine, so tangent would be negative, so that would be negative infinity. So, and pi is right here, to the left of pi, this function goes to negative infinity, right here. Now to the right of pi, when we come this way, then sine is a negative number, so it's going to be in the numerator, we're going to have some negative number, right, a small negative number, and then minus, cosine still would be negative, but would be a bigger negative number, right? Because when you're close to pi over here, sine is smaller than cosine in absolute value. So it would be really a small negative number plus a big positive number, bigger positive number. So it would be positive. Again, the sign of this is determined by the tangent, by the denominator. But over here, sine and cosine are negative. So negative over negative would be positive. So tangent is positive. So this would be a positive number over a positive number, so it goes to positive infinity, as you see over here, to the right of pi. So the limit of this thing to the left of pi goes to negative infinity, to the right goes to positive infinity, so we say the limit does not exist, right? So obviously it's discontinuous at pi, but what kind of discontinuity is infinite? Because the denominator goes to 0, but the numerator doesn't go to 0. All right. Decide if the function is continuous at 1. If it is discontinuous, what type of discontinuity is it? Is it discontinuous at 1? Yes, because 1 makes the denominator 0 and you can't have 1. But what does it do to the numerator? Well, also makes it 0. So in order to find what type of discontinuity, we have to actually find the limit. So what is the limit? Well, the limit, again, with the trick of factoring, again, we have what is negative 1. So this is a removable discontinuity because limit exists, right? So here is a hole in the function. That's the graph of this function. And we can define f at 1 to be negative 1 to remove that discontinuity, right? All right. Composite function theorem. If f of x is continuous at L and the limit of g of L when x approaches a is L, then the limit of f of g of x equals to f of limit of g of x. So basically means the limit of a composition of two functions. So the limit of f compose g of x is f compose limit of g of x. So we put the limit inside as an input for f of x. So the limit of f compose g of x is f compose limit of g of x. That's the idea. So here is evaluate this limit. So the limit of cosine of this, so you can think of cosine as a function and then x minus pi over 2 as a function. So the limit of a composition of cosine and this function is cosine of the limit of this. So we put the limit inside the parentheses, right? So limit of cosine of x minus pi over 2 is cosine of the limit of x minus pi over 2. And then limit of x minus pi over 2 when x approaches pi over 2 is just pi over 2 minus pi over 2, which is 0. So it's cosine of 0, which is 1. Right? We can do that only if f of x is continuous at that limit. That means cosine has to be continuous at the value of the limit that we get here for us to be able to use this method, right? And it is. We know cosine is defined as 0 and is continuous at 0. So cosine of 0 is 1. Trigonometric functions are continuous over their entire domain. So any trigonometric function is basically continuous over its entire domain. Now, to show that it's continuous at every real number, we must show that cosine, limit of cosine for any a in the domain of a, in the domain of cosine, for any a value in the domain of cosine, the limit is cosine a. Right? To do this, we're going to use this identity in trigonometry. That's cosine of something plus something equals to cosine cosine of these two minus sine sine. That's the identity from trigonometry. So here, to find the limit of cosine when x approaches a, we say we're gonna do some algebraic acrobatics. So in algebra, if you have a structure that you don't like, you want to change it, you can always multiply it by 1, and then of course 1 takes all kinds of form in algebra. 1 could be anything over itself, so you can multiply this by that structure, whatever it is, you know, like x minus 1 over x minus 1, and change the form of it without changing the value of it. That's one trick we use in algebra. Another trick is to take a structure that you don't like, add something to it, let's say some structure, and subtract the same structure. So if you add and subtract the same thing, you don't change the value, but you do change the form of it. So these are the two tricks we use in algebra to change the form of something we don't like or we want to change. So here, in order to change this, we are going to add and subtract a, because we want to get a involved in the argument of cosine. So we write the argument of cosine as x minus a plus a. So we use this trick here. So now we are going to group this into x minus a plus a, and we're going to assume that this is our alpha and this is our beta. So what's cosine of alpha plus beta? Well, it's cosine alpha times cosine beta minus sine alpha times sine beta, right? That's it. So instead of finding limit of cosine of that, we find the limit of this. And now, remember we said that limit of a difference is a difference of limits, and limit of a composition, we just put the limit inside. So we're going to do that. So we're going to take this limit right here. So this is one limit minus another limit, right? So we're going to write this as limit of cosine of that minus limit of sine, this whole thing, right? And we're going to write these are two different limits, because limit of a difference is the difference of two limits. And I'll write this as, we put the limit inside and take the cosine out, right? So we get cosine of limit, right? And then over here, we can take limit of sine, so we put the sine out, so we say sine of limit of x minus a, and then times sine alpha, right? So this way, we don't have to take the limit of cosine alpha, because limit of cosine alpha Cosine alpha is a constant compared to what? Because it doesn't have x. We want x to approach a, and if something in the structure doesn't have x in it, it's like a constant. So we keep it as a constant. And even if you put a limit here, it doesn't change anything, because limit of cosine a when x approaches a is just cosine a, right? Because the argument of cosine doesn't have x, so no matter what x does, cosine x remains cosine x, right? Same is true for sine a. Okay, so these remain cosine a, sine a. And now, what's that limit when you substitute a for x? Well, that's 0. So that would be 0. So that's cosine of 0 times cosine alpha minus, what's the limit of that when you substitute a for x? Is 0. So sine of 0 times sine alpha. Now we know sine 0 is 0, so that eliminates that. And we know cosine 0 is 1. So it's 1 times cosine minus 0 times sine, which is cosine. So what did we just prove? We proved that limit of right here, limit of cosine x when x approaches a is cosine a. That means no matter what a is in the domain of cosine, the function is continuous at that point. So what we can say is that cosine is continuous everywhere in its domain. And since the domain of the cosine is all real numbers, we say cosine is continuous everywhere, right, for real numbers. We can do the same thing for sine and for the rest of them. So the proof of sine is similar, but the rest of them we can think of, because remember, we have sine, we have cosine, and we have tangent, and then we have cosecant, and we have secant, and we have cotangent. But all of these are related to what? Sine and cosine. So if we know about sine and cosine, we can talk about limit of quotient and use limit of quotient to find the limit. And since we know these two are continuous, we can find that, prove that the rest of them are continuous in their domain, right? For all domain values. So we're not going to prove the rest of them, only sine, cosine was good enough. All right, so find the values of k that makes the function continuous over the given interval. So what we have to do is, we have to find the limit. So what is the limit? So the only point that this may not be continuous at is k, right? Because k breaks the domain into two parts, right? Numbers less than k and numbers all the way from k to 8, right? So let's find the limit of this. What's the limit of f of x when x approaches k from left? Well, we have to use this. So it would be 3k plus 2, right? From left, because we have to use that. We just have to substitute, right? Now, what is the limit from the right when x approaches k from the right? Well, from the right, we have to use this one. So that would be 2k minus 2, right? Now, what is f at k? So f at k, we have to use this one again, is 2k minus 2. Now remember, for this to be continuous at k, limit of f of x when x approaches k has to equal to f of k. F of k. Now, we know for the limit to exist, these two have to be equal, and they have to be equal to that, right? So basically what we have to do is we have to set those equal to each other. So let me show you the work right here. So limit of f of x from left is 3k plus 2, from right is 2k minus 3. And we set them equal to each other, and we find that k equals to -5. So if k equals to -5, then we have what? We have a function that is continuous over the entire domain here, right? Numbers from -infinity, so the domain is from -infinity to 8. So over this domain, this function is continuous because we found k is -5. All right, intermediate value theorem, what is that? Well, intermediate value theorem says that if a function is continuous over a closed bounded interval AB, so here's the closed bounded interval AB. Closed means A and B are included here, right? If Z is any real number between f of A and f of B, so here is f of A and here's f of B. So intermediate value theorem says that if you pick any number between f of A and f of B, you have to be able to find, right, some number C from A to B in this interval such that f of C equals to that number. So that's intermediate value theorem. There has to be a point here such that f of C equals to that number. So you can pick any number. Let's say you pick this one. Then there has to be a C such that f of that C equals to what? Equals to that number. So that's intermediate value theorem. So it says there is no value over here in this function over 0 to 4. It says there is no value of x such that h of x equals to 10. Although h of 0, although 10, so let me explain it here. So we got 0 to 4 right here, and at 0, this at 0, because 0 is less than 2, we have to use that. So 3 times 0 is 0 minus 4 is minus 4. So at 0, the function is right here, right? And at 4 is 5 plus 4 times 4, 16 is 21. So it's over here somewhere, right? So that means from -4, and this is 21. So that's f of A and that's f of B. But 10 is right in the middle somewhere. How come we cannot find any number between 0 and 4 that satisfies this? How come we can't find any number such that h of that number equals to 10? Does it violate the intermediate value theorem? And the answer is no, right? The answer is no. Why? Because intermediate value theorem has continuity condition, right? That means the function has to be continuous in this interval in order for you to be able to use that theorem. But for h of x, this function is not continuous over 0 to 4. It's not continuous at 2. Because look at the limit from the left. Is -4, from the right is 21. So that means this function is not continuous in this interval, so intermediate value theorem does not apply here. Okay? All right. Now you can, again, let me show you how you can do this. We can use the program that I talked about here. Let me close and reopen it here, so I don't have to work with that. So here we go. So with GeoGebra, you can actually graph these things where you want them. So you can put a condition on it. So suppose I want to graph 3x minus 4, right? So I want to graph 3x minus 4. See if I can move this a little bit. About right here maybe. So what I can do is I can do if a statement. So if, so here you go, let me do this first. So I'm going to create two functions. I'm going to create f of x equals to 3x 3x squared minus 4. Let me do that. So f of x equals to 3x squared minus 4, right there, right? And then the other one is 5 plus 4x. I'm going to create, let's say, g of x. I'm going to create g of x. I want to make it 5 plus 4x. So 5 plus 4x. Now, of course, I'm going to turn these off. So I'm going to click here, turn them off. Now I'm going to put a condition on it. I say if. So if we put if, there's an if. It says, what's the condition? I want to graph f if x is less than or equal to 2. So I'm going to put x less than or equal, you can get it from here, less than or equal to 2. I'm going to put 2 there. And then I'm going to put tab and graph f there. Okay? And then I'm going to graph g when x is greater than 2. So I'm going to put another if, and I'm going to put condition that x is greater than 2. Greater than is on your keyboard. And then g, graph g, like that. All right? So let me make it a little bit zoom out so we can see the functions. Oops. So you see what the GeoGebra did. We graphed the blue one where I wanted it, and they graphed the red one where I wanted it. So you see there is a gap right here, and this function is not continuous from 0 to 4. So that's why you cannot find 10, because 10 is in the middle that is not defined actually, right? There is no y value at 10. So that's the idea of intermediate value theorem. So let's see. So now we want to talk about the precise definition of